Hello everyone. In this video, we will learn about rotational spectroscopy. Rotational spectroscopy is also called as microwave spectroscopy because it is obtained by irradiating the molecule with microwave radiation. Microwave spectroscopy is concerned with transition between rotational energy levels in molecules. These spectra are shown by molecules which possess a permanent dipole moment. For example, HCl, carbon monoxide, water vapor, nitric oxide, etc. Those molecules having the permanent dipole moment will possess microwave active. Homonuclear diatomic molecules such as hydrogen, chlorine, etc. they do not have permanent dipole moment. Hence, they are microwave inactive. Let us derive the equation for moment of inertia of diatomic rotator and also the energy levels. The formula to derive the energy levels for rotational spectroscopy. Consider a diatomic molecule having the atoms of mass m1 and m2. They are in the equilibrium bond length of r. And also consider it rotates about the axis passing through its center of gravity. So when you consider the molecule, diatomic molecule of mass m1 and m2, its center of gravity will be lying somewhere here. So we are considering that it rotates about the axis passing through this center of gravity, and they are separated by the distance between the m1 atom number 1 and atom number 2 is r. So from the center of gravity, atom 1 is lying at the distance of r1 and atom 2 is lying at the distance of r2. At the center of gravity, m1 r1 equal to m2 r2. So our moment of inertia I is given by I equal to summation of mi r I squared for the whole range of I. Here for diatomic molecule is considered I equal to m1 r1 squared plus m2 r2 squared. Consider this as the equation 2 and consider the m1 r1 equal to m2 r2 as equation 1. So substituting the value of 2 in 1, so we get I equal to m2 r2 r1 plus m1 r1 r2. I equal to, taking the common term outside, r1 r2 will be coming outside and what will be there in the bracket is m1 plus m2. And also we know that r equal to r1 plus r2. Take this as equation 4 and the previous one as 3. Taking the equation 1 and substitute the value of r from equation 4 there. So m1 r1 equal to m2 r2, which is equal to m2 into r minus r1. m1 r1 equal to m2 r minus m2 r1. m1 plus m2, taking the common term outside, that is r1 outside. So you bringing this m2 r1 in this side, we will get m1 plus m2 into r1 equal to m2r. So r1 is equal to m2r by m1 plus m2. Similarly, we can also derive the value for r2. So r2 is going to be m1r divided by m1 plus m2. Substitute the value of R1 and R2 in equation number 3. We get I equal to M2R divided by M1 plus M2 into M1R divided by M1 plus M2 into M1 plus M2. So we can strike out the common term. So what will be remaining is I equal to M1 M2 divided by M1 plus M2 R squared. So here the term M1 M2 by M1 plus M2 is our reduced mass. So I becomes mu R squared now. So this is the final equation for moment of inertia calculation. Okay, the angular momentum of the diatomic molecule is given by L equal to I omega, where I is the moment of inertia and omega is the angular velocity. The angular momentum is quantized. So L equal to root of j into j plus 1 h cross, where j is the quantum number, rotational quantum number, that where the value varies from 0, 1, 2, etc. So for calculating the energy of a linear molecule, so energy will be half mv squared. Here we are considering the rotating molecule, so the value becomes half I omega squared. Multiplying and dividing or multiply the numerator and denominator by I, you will be getting I omega squared divided by 2I. Substituting the value of I omega squared, that is the value of L here, j into j plus 1 h cross squared by 2 pi. E equal to j into j plus 1 divided by 2I h squared by 4 pi squared. So the term now becomes E equal to h squared by 8 pi squared I j into j plus 1. This is the energy, it's given in joules. So we need the energy in terms of inverse centimeter when we talk about rotational spectroscopy. Hence we have to divide the whole term by hc. So now the equation becomes energy in terms of inverse centimeter is equal to h by 8 pi squared IC j into j plus 1. So replacing the whole term by another constant, that is called as rotational constant. So the equation now becomes, the rotational constant is denoted by the symbol B. So the energy in terms of inverse centimeter becomes Bj into j plus 1, where B is h by 8 pi squared I into c. So we have to remember this equation. So this gives the relation between rotational constant and moment of inertia. So if you know the moment of inertia, then we can calculate the rotational constant or vice versa.